So, dear students, today we will discuss another method of the uh, kinematics of a rigid body, analyzing the kinematics of a rigid body. This is the last method, and this method is basically termed as the instantaneous center method of velocity analysis. Now, as the name suggests, you can understand that basically this method, we see that this particular method is actually applicable for only doing the velocity analysis for a rigid body or for a group of rigid bodies, assembly of rigid bodies. We can only calculate the velocity of a point belonging to a rigid body if we know certain information regarding it. So that's why it is termed as the only applicable for the velocity analysis, and it is to be understood that this method cannot be applied to follow the to find the acceleration analysis of a mechanism or a system of rigid bodies or a rigid body. So that is the drawback of this method. But so far as the velocity analysis is concerned, this method gives sometimes a very quick result. So that's why we need to study this instantaneous center of velocity method. Apart from that, it has certain physical meaning as well, so which will be helpful for us in our future kinetics of and study of kinetics of rigid body. So as I said that this method is applicable for the velocity analysis only. The instantaneous center of velocity, or sometimes known as the center of rotation, is defined as the point about which the any rigid body is assumed to be rotating at least instantaneously. So we see that, suppose for our, so far as our kinematics of a rigid body is concerned and its geometries of motion, so we see that the motion can be translational. Obviously, when a rigid body is executing a translational motion, there is no chance of finding out the instantaneous center of velocity for this. In fact, for such translational motion, the instantaneous center will be located at an infinite distance away. So that will be of no use for us. However, if a rigid body rotates, it undergoes fixed axis rotation about a point, then we know that we do not have to carry the instantaneous analysis center. We do not have to find out the instantaneous center, because that point of rotation, the fixed point of rotation, or so to say the center of rotation, that means the point about which the body is rotating about the fixed axis, will itself will be the center of rotation, and that will not be instantaneous. In fact, it will be all through during the period of motion, since the body is rotating about that fixed point. So obviously that point will be permanent center of rotation. So it is not instantaneous center of rotation. So actually the third case of motion of a rigid body, where we know that the body is executing a general plane motion, as we know from our previous knowledge that a GPM, or a general plane motion of a rigid body, according to Chesel's theorem, can be assumed to be considered as a combination of a translational motion and a rotational motion about a point. So for this GPM, that means the general plane motion of a rigid body or a system of rigid bodies, actually this instantaneous center of velocity or center of rotation is basically applicable. So as we see that this center point, that means we will assume that the body is rotating about this center, and we call it as to be center of rotation. But unlike the case when the body is rotating about a fixed point, we know that that particular point will be always the center of rotation. But in this case, actually this point is instantaneous. In fact, at that particular instant, the body is assumed to be rotating about that point. So after time delta t, we see that this point will no longer remain to be the center of rotation of that rigid body. So it is therefore applicable at a particular instant of time, and that's why it is termed as the instantaneous center, or IC. It is abbreviated as IC, instantaneous center of the rotation of the body. So let us consider, say, the following body which is undergoing a plane motion. I mean to say it's undergoing a general plane motion, for which we know completely the velocity of one point of the body, and we need to find out the velocity of any other point for which we know at least its direction. By this method, we can find out the angular velocity of the body, and also we can find out the velocity of any other point after locating the instantaneous center, any other point on the body, any other point on the rigid body. So we can say any other point on the rigid body after locating the instantaneous center of rotation. So for that case, let us take this example. Suppose that this is a rigid body which is undergoing a general plane motion, and let us suppose that we consider the point A belonging to the body, for which I know completely the magnitude of the velocity of this point, I know its direction and know its sense. So let us call that this is the velocity. That means, in short, the velocity vector for this point A is completely known to me. And for example, let us consider we have another point B for which I know the direction of the velocity of the point B. Let us suppose that this blue line, this represents the direction of the velocity for the point B. But I do not know the magnitude of this velocity of the point, neither we know the sense of the velocity of this point. So I know only the direction, and for the point A, I completely know the velocity vector for the point A on this body. So at this situation, our objective will be to find out the velocity of this point completely, and also our objective will be to find out velocity of any other point other than A and B on this body. Let us see how we can do. Now, first of all, since we will assume that the general plane motion can be considered as to be a rotation at least instantaneously about some point, therefore it is obvious wherever that instantaneous center of rotation be, it is obvious that instantaneous center of rotation, the distance of the point from that point will be always going to be perpendicular to this velocity, because we assume that about that instantaneous center, the whole body is instantaneously rotating. So since we know that if we have a rotation, say rotational motion, we know that if this is the center of rotation, then we know that actually you see that if I join this point A, what will be the velocity? We know that the direction of the velocity will be, at least you know, it will be perpendicular to the line joining the center of rotation to that point. And the sense will be depending upon the sense of rotation of the body. So if this is the sense, obviously the sense of velocity will be this. But what is important is that this line joining the center of rotation to that point will be perpendicular to the velocity vector. So if this red line is the velocity, known velocity vector for the point A, so I can draw a line, this the blue line here, this is actually the indigo line, is known, you see it is drawn perpendicular to the velocity vector. Say it can be produced in this direction or that direction, of course. Now, since we know for the point B what is the direction of the velocity of B, so I can draw similarly another line perpendicular to this direction and allow these two perpendiculars to come and intersect at this point. Let us call this point as point O, and this point O we will call it as to be the instantaneous center of rotation. That means for the instant when the velocity of this point A of the body is directed this way, I know its magnitude, I know its direction, I know its sense. Under such circumstances, if this will be the direction of the velocity for any other point on the body, I know that in that case, we see this is the point O about which the body can be assumed to be rotating, and the sense of rotation will be obviously in this direction. So this will be instantaneously the angular velocity of the body. So I can therefore say that if I know the velocity, I can geometrically construct these perpendiculars and thereby locate this point I. Sorry, this is the not the point O. It is already defined as the point I. Sorry. So I say that these two perpendiculars are intersecting at this point I, which I call as to be the instantaneous center of rotation. Now we can, of course, from here find out the magnitude of the velocity. So we see in the above, suppose we know the velocity of a point A completely, and for any other point, say B, only the direction of VB is known. We draw perpendiculars to VA. You see this perpendicular to VA, and the direction of line of VB, that means this is the direction, it is known. Let us suppose that this direction is known for us, and these two perpendiculars allow them to intersect at the point I, which will be the required instantaneous center of velocity at this instant. So obviously I can find out the angular velocity omega at this instant. So this is called the instantaneous angular velocity. This omega basically will be termed as, this will be termed as the instantaneous angular velocity. We can say at this instant, instantaneous angular velocity, because angular velocity can also vary. So that's why it is instantaneous. At this instant, this is our omega, and we can find out this omega. How we can find it out? Just apply the theory of rotational motion that we have learned in our school days physics, that omega will be equal to the magnitude of this velocity divided by this distance. That means it is VA divided by IA. That will be our omega, which will be termed as to be the instantaneous center of instantaneous angular velocity of this body. So once we find out omega, then I can find out this magnitude of VB. How we can do it? It is pretty obvious that VB will be equal to omega into IB. So again, following that theory of rotational motion, that will tell us that the magnitude of the velocity of point B will be omega into this distance called IB. So omega, in place of omega, I can put this expression, and I can say that VB will be equal to VA into IB divided by IA. And what will be the sense? The sense will be incommensurate with the sense of the rotation of this body. See, this is the sense of VA, this is your IA. So naturally omega will be this clockwise sense, will be the sense of angular velocity, instantaneous angular velocity of this body. So the sense of VB will be incommensurate with that sense of angular motion. So in that case, your sense of velocity of the point B will be, in this direction. So I say therefore VB will be equal to VA into IB by IA, and sense of VB must be compatible with the sense of VA and omega. Now for any arbitrary, so we therefore, we can therefore very easily from here, if we know this velocity, from there we can very easily calculate and find out the velocity of this point B. Magnitude, sense, direction, everything we can find out very easily. Now it will be our duty to take any other arbitrary point other than the points A and B on the body. Let's say this point is C, for which we do not know anything except its location. That means earlier for the point B, at least I know its location, and also I know at least the direction of the velocity of this point. But for point C, except its location, nothing is known to me. What I need to find out is the velocity for this point. So how we can do it? Now it is simple. since you know the location of C, since we have already located the instantaneous center, I have already found out the sense of angular velocity. So my thing will be to join IC, and after joining this line IC, I draw a line which is perpendicular to this IC, and then put that line will be this direction of the velocity for the point C, and its sense will be incommensurate with the sense of angular motion of this body. As a result, this sense will be in this direction, and we can find out what should be our velocity of point C. So we can therefore directly say that the velocity of point C will be omega times IC, and since omega is already known to be VA by IA, so I can put it to be equal to VA into IC divided by IA. So this is how we can actually find out for a rigid body, we can apply this simple method. It is basically a geometrical method, because you need to locate geometrically the instantaneous position of this instantaneous center of rotation, and the remaining things also. For that you actually need to construct lot of lines, lot of perpendiculars and everything, calculate these distances IA, IB, IC, etc., and then solve for the velocity for the case. Now let us take an example to show how we can apply this method to analyze for the velocity of a rigid body or a system of rigid bodies, or maybe a mechanism. Let us take an example. So we consider this problem from the book of Merriam and Craig. This is the problem 5 by 116. So this is the problem being given to us here. It consists of a system of rigid bodies. There are one rigid body here, then another rigid body there, then another rigid body there. So it is a system of 3 rigid bodies. Of course, these connections of pulleys and rollers are there, so we can also include them in our system, and all the relevant dimensions and the geometries are actually mentioned in this figure. So let us see what is the case. In this case, if this is the thing, we basically first describe the figure first. We have a plunger. This is a plunger. It can move upward or downward. Now to this plunger there is this rod. We can say this is a link. This link to the point D, there is a roller being fitted around this point. Actually, this roller will help this point D to move in the horizontal direction as well as in the vertically up down direction, right left and vertically up down. This motion of point D is possible because of this rolling contact with this one. So actually the other end of this link is also fitted with a small roller, which actually moves against the spring, against a spring which is fitted inside a slot which is perfectly horizontal. So it is pretty obvious that the point A is constrained to move along this horizontal direction. However, the point D will have both the vertically up down motion as well as horizontal left right motion. So this point's motion of point D is actually not constrained, and the entire thing is fitted with a crank, and the crank is having a permanent center of rotation. This is the fixed center or permanent center of rotation, and the permanent center of rotation for this crank OB is point O, and the dimensions are all prescribed. Let us see what is the problem. The motion of the roller A, so this is the roller A, small roller is fitted around here. Motion of the roller A against its restraining spring, so this is this restraining spring, is controlled by the downward motion of this plunger. So actually this plunger is moving down, so naturally this one will try to move towards right, but it is from the intuition we can say that if this end is pushed, so then this end will try to move towards right, so it will try to push the spring and moves against the resistance of the spring. For an interval of motion, for the velocity of the point E, that means this plunger's velocity is in the downward direction, this is small v, this is the downward direction, the magnitude of this velocity is mentioned to be as 0.2 meter per second, and we need to determine the velocity of the point A. We have to find out the velocity of point A when the angle theta, that means the angle between this crank and this connecting link, this angle, when this angle theta becomes equal to 90 degree, I have to find out what would be the velocity of the point A. Correct? So that is basically our problem. So here we will solve this problem by the instantaneous center method. It can be solved by other methods as well. I mean to say the relative velocity method. However, the absolute motion analysis may be little bit cumbersome here, but of course we can apply it depending upon the instantaneous geometry. We can apply this problem, find out the motion of this point by the absolute motion analysis method either also. So here we will solve this problem by the instantaneous center method, and we note that the directions of VA and VB will be, so this is the point VA, so that is actually known. The direction of the motion for the point A will be along this horizontal line, and the point B, its direction, the velocity direction will be always along this line, which is going to be perpendicular to this line OB. So actually, the velocity for the point B and for the point A, the directions of the velocity for VB and VA is completely known. So this will be the horizontal line, that will be the direction for the velocity of A, and this line, which will be perpendicular to this link, that will also be actually the direction of VB. Hence we draw a vertical line through the point, since you see that this the velocity is the direction is completely known. So what I can do, I can draw a perpendicular line like this to this direction, and of course I can extend this line, because this is going to be 90 degrees, so I can extend this line and allow them to meet somewhere here to find out the instantaneous center for this this mechanism. Actually, this construction is shown here like this. So this is for any general angle, the construction is shown. You see, this is your point A. So this line is drawn, which is 90 degree to this line, and this OB, because we have seen that the direction of velocity of point B will be perpendicular to this line OB. So therefore the OB line itself will represent the OB line will be itself actually, if we consider this link ABD, for that we see, consider this link ABD, then for that since this velocity will be perpendicular to this line OB, so the instantaneous center wherever it will be along this line. So therefore this line and this line will come and intersect at this point. We can call this point as I. Now in order to find out the velocity of point D, what we will need to find is to draw this line ID, correct? And perpendicular to it, you see, this is the perpendicular, this red line, this will be your velocity of point D. So this will be velocity of point D, for which its vertical component will be this velocity, and that should be equal to your small v. So this vertical velocity, the component of this red vector along this vertical line, this must be equal to v. So this is equal to v. So this is the construction for the case where theta is any arbitrary angle. The same construction is repeated here, considering this theta here, that is equal to 90 degree. So considering this theta to be equal to 90 degree, we see therefore, considering this angle theta to be 90 degree here, we can see that this construction is being repeated. So I just once again tell that I draw a perpendicular line, this is the perpendicular to the VA direction, and this comes, I draw first perpendicular to this line, OA, and then I extend the line OB, allow them to come and meet at point I, which will be our instantaneous center. So I here will be my IC. This is the instantaneous center. Now I join this ID line and perpendicular to it. That means this line is going to be perpendicular. So VD will be perpendicular to the line ID, and the component of this vector along the vertical direction, this pink line, is actually being given to be equal to 0.2 meter per second, which is actually our small v in this problem. Under these circumstances, so we do not have to focus on this geometry. Here it is for the case where theta is any other angle other than 90 degree, this will be the geometrical construction. But for us, we need not focus on to it. We should take for us, because we will have to consider theta to be equal to 90 degree. So we see that this will be our construction. So very quickly, therefore, we say that if this angle is phi, then this angle must be equal to phi, and we define this angle as beta, and I define this angle as 90 degree minus beta. So as a result, this small angle, that means the angle that this velocity of the point D will make with the vertical direction through D, will be also equal to this angle, that means 90 degree minus beta. So our objective will be thus, to find out this geometry. So it is pretty simple to note that we see from here that the distance OB is specified for this. The distance OB is known to be equal to 90 millimeter, and the distance AB, that is known to be equal to, you see, this is the distance AB. This distance is known to be equal to 120 millimeter. So if this is 90 millimeter, if this is 120 millimeter, then obviously the distance OA will be equal to 150 millimeter. And once I find that, we can take this small triangle to identify that if this is phi, then my tan phi will be equal to 4 by 3. That means how it is coming, because tan phi will be equal to AB divided by OB. AB is known to be equal to 120. OB is known to be equal to 90. So it is pretty obvious that tan phi will be equal to 4 by 3. Again, tan phi can be written as, that will be equal to IA divided by OA. So from here I can say that IA will be equal to tan phi multiplied by OA. OA is known to be equal to, we have just now calculated that OA is equal to 150 millimeter. We have just now shown that OA is basically equal to 150 millimeter. So if this is 150 millimeter and this is tan phi 4 by 3, it is obvious that IA will turn around to be 200 millimeter. So that will be the angle that we can get. So once I know this, this is to be equal to 200 millimeter. Once I get this, now my objective will be, of course, to actually, find out this angle beta, for this. And in order to do that, what I see from here, because, if you look at this triangle AID, now focus on this triangle AID, for which I know the angle between the line AD, whose dimension is also known to us. Why it is known? Because we know AD must be equal to 120 plus 60. That means AD must be equal to 180 millimeter. That means here, you see, this AD is equal to 180 millimeter. That has already been given. So I know the distance AD, which is 180 millimeter. I know the distance AI, which is 200 millimeter. And I know the angle between AD and AI. So it is therefore for us, it is simple actually, to find out, to apply the cosine rule to this triangle to find out what will be the distance ID. So therefore, we apply the cosine rule to this triangle and find out the value of ID. That means this distance, that is equal to 170.88 millimeter. Now, once this distance is found, I need to know this angle. So what I do, I can apply to the same AID triangle the sine property. So I can apply to this triangle the sine rule. So if I apply the sine rule, it is pretty obvious that 170.88 divided by sine phi, for which tan phi is known to be 4 by 3. That means sine phi will be equal to 4 by 5. So it is ID divided by 0.8, because sine phi will become 0.8. So ID means 170.88 divided by 0.8, that must be equal to 180 divided by sine beta. Correct? Because AD is 180 and this angle is this. So just apply the sine rule to this triangle and we get that sine beta turns out to be as 0.843. So once this is known to be sine beta is known, we can come here, we see that this angle will become 90 degree minus beta. So this is 90 degree minus beta, and the unknown velocity, that means Vd, its cos component is equal to 0.2 meter per second. So I mean to say that Vd cos 90 degree minus beta means Vd sin beta is equal to 0.2. That is completely being given. And I also know sin beta. So obviously from this I can find out Vd. That will be 0.2 divided by the sin beta, and the velocity of the point D is completely known. That is 0.237 meter per second. So our therefore objective that to find out the velocity of point D, that is actually, we have found out the velocity of point D. But our objective is to actually find out the velocity of point A. And obviously we see that its direction, because the direction here is specified. So if this is going to be in the downward direction, this black vector must be in this direction. So it means that this link ABD, is actually, trying to rotate, in this direction. So it is trying to rotate in this direction. That means in the anti-clockwise sense. So quite naturally, the velocity of point A will be towards right, because it needs to be consistent with this angular velocity of the body. So as a result, we can find that the point A's velocity must be along towards the right direction, and I need to calculate this distance IA. It is already known to be 200 millimeter. So it is pretty simple that the velocity of point A will be equal to velocity of point D that we have just now found divided by this distance ID that is also being found for us, multiplied by the distance IA, which is completely known to me. So therefore velocity of point A will be equal to, Vd by into IA divided by ID, and we see that it will be 0.237 into 200 by 170.88, and we turn out to be as 0.2774 meter per second, and that velocity should be towards the right direction. So it is therefore seen with this simple example that we can very easily, find out the instantaneous, with the help of this instantaneous center, we can very easily find out what should be the velocity of this point. Actually, this instantaneous center, instantaneous center method will give us a very quick solution for the problem. But here I have some instruction that for the above problem, try to find out the velocity of point A as a function of theta. That means here we have solved this magnitude of this velocity, as well as we have found out the direction also, everything that has been done for theta equal to 90 degree. But if theta is any other arbitrary angle other than 90 degree, what should be this velocity as a function of theta? You can try at your home to find out. And you need to remember that the instantaneous center of velocity is not the instantaneous center of acceleration. That means for acceleration analysis also, we can find out the instantaneous center for acceleration, but that is not very much popular as the instantaneous center of velocity is. Therefore we will not pursue to find out the instantaneous center of acceleration, but it is to be clearly kept in mind that never the instantaneous center of velocity will be the instantaneous center of acceleration. So you see, this instantaneous center of the velocity method is very much helpful for us, particularly the rolling particularly the rolling motion problem. So let us consider that we have a disk, something like this, suppose, which is actually, it is moving on a flat surface, and this rolling motion takes place without slipping. So if suppose we know the center point of this roller, suppose if I know that this is your omega with which it is rolling, then we can find out, you see, the any point within the body, correct? We have already done it analytically, that means by following the absolute motion analysis we have found this problem, solved this problem. But here also we can do this, that means if I know this location of this CA, then I can calculate this by this instantaneous center method. That means, you see here, this is the point, actually this is the point which is the instantaneous center of rotation for this rolling motion without slipping, because this is the point which is having zero velocity. So actually this point of contact between this roller and the horizontal surface, this point of contact is serving the instantaneous center of rotation for this disk at this instant. So what I can do is simple, I can just join these 2 points C and I, simply join these 2 points. Since your omega is being given in the clockwise direction, so it is pretty obvious that our velocity of point C will be, in this direction. So this will be going to be my velocity of point C. We can write it as VC. Now, in order to calculate the velocity of the point A, what I need to do is simply join this IA. So simply join this line. So we can join these 2 points here like this. I can join it, and now you see this is the sense of rotation is in the clockwise sense. So what I need to do is to draw a line which will be going to be perpendicular to this line. So we see that if we draw this line which is perpendicular, and since the sense is known to be the clockwise, so it is pretty clear that this velocity will be, it should be actually 90 degree to this line. So this is going to be 90 degree, and the sense of this motion will be, of course, this will be the sense. So let us take the sense of motion for the point A. This will be the velocity of point A. So you see, this velocity of point A is completely known. So if actually, this distance is called R, this distance is called R, this distance is known to be equal to E, and of course I know this angle. That means this angle, this line CA is making with the horizontal line, say this through the center. Let us suppose that this angle is known to be equal to theta. Then it is obvious from this relation I can find out the magnitude of IA, and that can be done by simply following the cosine rule to this triangle. So we can say that IA must be equal to, that will be equal to R square plus E square minus, it is twice R into E into cos of 90 degree plus theta. So that will be going to be my, the application for the cosine rule here. So in this case, I can find out the value of IA. So IA is thus equal to, it is R square plus E square, and this is cos 90 degree plus theta is minus sine theta. So it will be therefore plus twice RE into sine of theta to the power half. That is going to be our distance of IA. So it is clear if this is omega, suppose this omega is known to us, then we can find out from here that velocity of c will be equal to omega into r, correct? And the velocity of point A, that must be equal to omega into this distance. That means omega into root over r square plus e square plus twice re into sine theta. Now we can actually change this angle and we can find out correspondingly. We can also have this e also. That means, for example, if I am trying to find out from this formulation what would be the velocity of this topmost point on the disk, that means if I call this point as B, so what would be this velocity? It is pretty simple. By instantaneous center method, the velocity will be, it's the velocity will be along this direction. First of all, must be perpendicular. Secondly, you see this must be, actually omega into this distance, that is ib. So it is actually equal to 2r into omega, or we can say, because this is r, this is also r, so it will be 2r into omega. So it should be twice the magnitude of, or we can say this is twice the magnitude of the velocity of point C. And also this can be found from this equation also. In this case, for point B, we can say for point B, for our formula, for point B, we see that E becomes equal to R. Secondly, theta becomes equal to 90 degree. So since E becomes equal to R and theta becomes equal to 90 degree, so we see from here that gives us the velocity of A will be equal to omega into R plus E. First of all, omega into R plus E. Since E and R are equal, so it is becoming equal to twice omega R. So we can check that our equation is correct or not. That we can do by joining this. So in this manner, in fact, we can find out the velocity of any point on the disk by this instantaneous center method of finding out the velocity. So this actually, shows us how quickly we can solve our problem. For example, this is another example that we have talked about. This is another example that we have talked about. So we can say this is example 2, and we can of course show another example, for a mechanism which is very common in mechanical engineering. That is what is termed as the crank connecting rod mechanism. So this is another example. We can consider this to be an example 3 here. So that is sorry, that is another example we can think of. That is, we know, suppose we are having a crank. Let us consider that we are having a crank and the crank is driving, suppose a piston which is somewhere here. So this is the piston, it is driving, and we know that here this it is not exactly on the line of center. You see this distance, let us say this distance is known to us. This distance is known to be equal to E. Let us suppose this is R and this angle is known to be equal to theta. And we know this distance, and of course we also calculate. We know this is O. Let us say this is O, this is A, this is B, this is B. And also let us suppose that AB is known to be equal to L. And at the instant when, suppose this one crank is rotating in this direction with an angular velocity of omega, what should be the corresponding velocity of point B? So in order to do this analysis, let us take this little bit downward for us, this way. So this is the case. So in order to analyze quickly that if all these dimensions are known, so what would be, let us, our problem is find the velocity of point B, velocity of slider B, slider or piston. You can say this is the piston also, piston B. We can find it out by the instantaneous center method. How we can do it? Again, we see the direction of B is defined. That means, you know, that it will be going to be along this horizontal line. So what I can do is we can draw a perpendicular line through it like this. Sorry, we can draw the perpendicular line in this manner. So this is the perpendicular line, and also we extend this OA line like this. You see this, let me take the extension this way. So this is the extension. It is because we are trying to actually locate the instantaneous center of the link AB, correct? Because why this is the extended? Because we know that the velocity of point A at this point should be along this direction, which is going to be, you know, this angle is going to be 90 degree. So that's why we extend this line, allow this to come and intersect this point as I. So we see that from this geometry, from the geometry that is being given, that means if I know this dimension R, if I know this angle theta, correct, and if I know this distance L, and if I know this distance E, then obviously from here we can actually, we know that we can actually find what should be this, you know, this distance IB. In order to do that, we need to solve this triangle. We need to solve this triangle here, the given geometry here. We see that this angle is being to be equal to theta. So since this angle is being equal to theta, we can, of course, we can say that this we can find out from this scale diagram. We can locate what should be the dimensions of IB. So this IB needs to be calculated. This IA, of course, needs to be calculated, and then we can find out the velocity of this point B, and that can be done. You know, the velocity will be directed like this. Sorry, let me just take this. Let me say that the you know, this can be found this way. So if this is VB, then it is pretty clear from here that VB should be equal to omega into R, that is going to be equal to our VA into, this will be IB divided by, this will be IA. So IB divided by IA will give us this thing. Now IB by IA, once if you see here, I can call this angle. In fact, from this geometry, whatever geometry is being given for us, I can actually calculate this angle. I can calculate this angle. That means this connecting rod is making with this horizontal line. I can call this angle as to be equal to phi. How we can calculate it? It is pretty simple from this geometry, that L sine phi, from here we can write it like that. From the geometry we can say that L sine phi minus this distance E, correct, that should be equal to your R sine theta. That should be equal to R sine theta. So L sine phi minus, because L sine phi will actually give us this value. So through this point, if I draw this line, so we see that this actually, this perpendicular is giving us this value called L sine phi. If we subtract from here, that will be E. So that will be the distance from here to here, and that must be equal to R sine theta. So from this relationship, if we know L, R, E and everything, from this relationship, we can find out the value of phi. So we can say that sine phi is equal to, from here it is E plus R sine theta, E plus R sine theta divided by, it will be equal to L. So from here I can therefore find what should be this angle called phi. So once I know this angle phi, from this geometry, we can say that this angle, correct, this angle is going to be equal to theta plus phi. So this angle is going to be equal to theta plus phi. So this angle is theta plus phi, that is being completely known to us. Now see this angle, this is equal to, you see that this angle is basically equal to phi. So we see therefore, since this is phi, this must also be equal to phi. From this small right angle triangle, we can say then that this angle, it is going to be equal to 90 degree minus phi. So everything of this geometry can be calculated if we can calculate the phi from here. So going back to this relationship, we can say since Vb equal to omega r into Ib by Ia, I can write this omega r into, now Ib by Ia should be equal to sine of, so we can write that it should be sine of theta plus phi divided by, it should be sine of 90 degree minus phi, that means it will be equal to cos phi. So we see therefore, since your phi is already known from here, we can further simplify this here. We can down the line simplify this, can write that Vb will be equal to omega r into this, we can write sine theta cos phi, and cos phi cancels. Sine theta cos phi divided by cos phi, so that cos phi we cancel it out. It will be cos theta into, this will be tan phi. Sine phi by cos phi means that it should be equal to tan phi. Now since sine phi is being given here, so we can say from this relationship that tan phi is going to be equal to root over L square minus, we can write like that, it will be root over L square minus E plus R sine theta whole square, and on the top we can write that it should be E plus R sine theta. So that is going to be our tan phi. So as a result of that, we can say from here that Vb will be equal to, we can put it all these things here and can find out the expression. So once this tan phi is known to us, we can substitute this tan phi into this equation, tan phi value into this equation, and can get what should be the velocity of this point. So you can simplify this expression at your home and should be able to find out what should be the velocity, provided we know all these geometries. That means we know the dimension OA is known to be equal to R, we know L, correct, AB is known to be equal to L, E is known, and of course E and theta both are known. So under such circumstances, we can find out for given omega what should be the velocity of point. In fact, if now someone defines another point here, let's say we define a point C here on this connecting rod, let's say this distance AC, this distance AC is also known. So this distance AC is known to be equal to say A. So I can find out the instantaneous velocity of this point also. For that, what we need to do is to draw this line from here. That means we need to join this IC line, and once this IC is drawn, we see that the velocity, let me draw it properly, say from point I, we need to join this point C. Let us slightly shift this point C here. Let's say this is our point C. This is the point C. Now if this AC distance is known, then of course we can find out the velocity of the point C as to be a vector which will be something like this, which is going to be, sorry, which is going to be 90 degree to this point C. So if we call this point as C, so this line, this small red vector, that will actually give us the velocity of point C, which will be perpendicular to this line segment IC. So if this AC is known, then we can find out this angle is known theta plus phi. So using the cosine rule, I can also find out this distance IC, because AC is known to be equal to A. So IC can be found because this angle is known. That means IC is equal to, IC will be equal to, we can write it here, that it will be equal to IA. IA is of course known. Previously we know this IA from this triangle. So IC can be calculated here. So once this IC is calculated using this cosine rule, we can find out, this will give us what should be the velocity of point C. So we can find out the point on the link AB, any point on the link AB for that matter. So students, therefore, with 3 examples, we showed you how the principle of this instantaneous center method can be applicable, can be applied to solve the velocity analysis for a rigid body or a group of rigid bodies or a system of rigid bodies. But once again, we need to remember that this is only applicable for the velocity analysis, and it cannot be extended to the acceleration analysis of the system. So with this, we stop our today's class here. In the next time when we will be meeting, we will start with the rigid body kinetics. Till then, it's bye from my end. Thank you.